Hello and welcome to the presentation of the paper Compressed Linear Algebra for Large-Scale Machine Learning by Stanford Scholar Initiative. In today's era, you must have heard about the revolution that big data and machine learning is bringing for us. Applications of ML range from self-driving cars to facial recognition to whatnot.
Many of the ML algorithms that are used are iterative in nature and perform repeated, read-only access to data.
They tend to rely on using matrix vector multiplications to achieve optimal model.
Each such matrix vector multiplication requires full scan of the data matrix. Combined with the huge scale of data that these algorithms work on, the whole operation becomes IO-bound. Thus, to increase performance, it becomes essential to fit more data into memory.
Let us now look at how some of the current solutions counter this.
A baseline solution that is used is to use a general-purpose compression technique to allow more data to fit in memory and then
Blockwise uncompress it while performing operations. The compression technique used can be either heavyweight or lightweight.
heavyweight compression tends to have high compression ratio, allowing more data to fit in memory, but with low decompression speed, making the in-memory execution slower. While lightweight compression, on the other hand, due to its low compression ratio, has a high decompression speed. Let us now look at the solution the authors of the paper propose.
This paper initiates the study of compressed linear algebra or CLA, in which database compression techniques are applied on data matrix to get compressed data, and then linear algebra operations are executed directly over the compressed matrices. Thus, while we saw that general purpose compression techniques struggle to optimize between compression ratio and decompression speed,
Compressed linear algebra, or CLA, achieves moderate compression ratio without any need to decompress the data.
let us now see the main ideas this paper proposes. The authors make use of column-wise compression for two reasons. Firstly, they argue that machine learning datasets have low column cardinality, meaning that number of distinct values per column varies, with a lot of columns having very few values. Secondly, a lot of columns in such datasets are correlated with respect to number of distinct value pairs. Making use of these properties, they encode a column as a list of distinct values together with a list of offset per value. For example, in the given figure, the given column is encoded as a list of distinct values 1, 2, 3, with each also containing the indices of the rows where they appear. To sum up, the authors exploit column correlation by encoding column groups together and combine this with three column encoding formats: offset list encoding or OLE, in which the list of offsets where a value occurs is stored as is; run length encoding or RLE, where the list of offsets is stored as a sequence of runs; and the uncompressed columns themselves as a fallback for high cardinality columns. Finally, the authors propose a sampling-based compression planning algorithm that can be used to output a good compression plan. Let us now see the evaluation and the experiments done by authors. The authors used Apache System ML and integrated CLA into it for the experiments. System ML takes in a compressor operator, compressing inputs according to compression planning. Several frequently used algorithms were used, like linear CG, linear DG, etc. These are some of the real-world datasets and the scale datasets that were used to draw results for the experiments.
The results were compared against uncompressed linear algebra, heavyweight compression using gzip, lightweight compression using Snappy, and another lossless compression technique using dictionary encoding called CSR.
These are the compression time in seconds that each compression technique took on the datasets. The following results for execution time were obtained from computation of matrix vector multiplication. CLA performs close to ULA except in cases of Higgs and MNIST datasets. This is due to the small size of the L3 cache, which is not able to store the output vector. There are huge improvements in compression ratio as compared to CSR-VI and D-VI formats. CLA was able to outperform both ULA and Snappy in case of some ML algorithms and also achieves almost equal performance with algorithms like PCA. Thus, the performance of CLA was found to be close to that of computation over uncompressed data. Compression ratios similar to gzip were yielded. At a lesser cost, reasonable compression time and compression ratios were achieved. So, let's sum up this presentation. The authors have thus initiated the study of compressed linear algebra, a CLA, which is able to achieve good compression ratios without any need to decompress. With this, we have come to the end of the presentation. If you would like to visit more of our talks, check out scholar.stanford.edu. Thank you.